Video on 1.2.5 of Stein's elementary number theory book, and it's kind of an overview of some of the study of how many primes there are. It's a super famous question. I guess we know that there's infinitely many, but what else can we say about them? And more importantly, how are they spaced? Do we have any idea about the behavior of the primes? How often do they occur? So we already know that there are infinitely many primes, and that was due to Euclid. And we just got done exploring that there's also infinitely many primes that have the form, say, 4x minus 1, or maybe more generally, of the form ax plus b, as long as a and b are relatively prime. And in this section, too, we'll encounter the ultra-famous Riemann hypothesis, but we won't say too much about it, just that it's related to the study of prime numbers in some way. So let's start off, though, maybe on page 15. And so here's kind of this kind of fun discussion about how do we measure the number of primes that we have. And so something like, what percentage of natural numbers are even? And the answer to that question is half of them. And the way that I might think about that is I might think about something like Z2 from a proofs class, which consisted of the set of the equivalence classes 0 and 1. And remember, another way to think about these is that this represents all the even numbers, and this represents all the odd numbers. Therefore, how many of my natural numbers are a half? How many of the natural numbers do I have are even? Well, they fall in this equivalence class, and there's two possibilities total, therefore 1/2. That's how I might think about that. Similarly, if I try to get rid of this stuff for you, what percentage, I'll erase that now too. Another fun way to think about what percentage of natural numbers have the form 4x minus 1. I think I tried to say in a previous video too. Well, I know all the natural numbers fit into one of these categories: 4x, 4x plus 1, 4x plus 2, or 4x plus 3, which remember, this is the same as something like 4x minus 1, right? Those have the same form. And so in that case then, well, how many natural numbers have the form 4x minus 1? We would expect that 1/4 of them would be, right? And so I'm trying to say that of the natural numbers, they could be split into these 4 categories, so this represents 1/4 of them that I've highlighted below. Now, some other more fun questions is, what percentage of the natural numbers are perfect squares? And I love this. The answer is 0% of all of them, in the following sense, if we use the limits. So let's think about the limit of the proportion of perfect squares to all natural numbers. And so what are we saying here? In symbols, right, the limit of the proportion of perfect squares to all natural numbers. Here, by the way, this pound sign is the notation that Stein uses for the cardinality of a set. So we're counting how many natural numbers are there that are less than a given number x such that n's a perfect square. So let me give you an example. Let's say x is equal to 25. And I said, hey, tell me all the perfect squares that are less than or equal to 25. You tell me 1, 4, 9, 16, and 25. And notice that there are 5 such numbers there. And so what we're saying, and we're not proving this by any means, it's a fact that has been shown elsewhere, that the number of perfect squares that are less than a given number x is actually about square root of x. And what I tried to do in my example is, hey, square root of x is 5, and notice that's how many perfect squares are less than 25. So there are square root of 25 perfect squares less than 25. And again, it's roughly that. I'm not saying it's exactly equal to, it's not like some glorious pattern, but it's roughly that. So in that sense then, to go back to this question, if I'm thinking about what proportion of, natural numbers are perfect squares, this is roughly square root of x in the top over x. And now we've got this calculus problem to solve. So if I took the limit as x goes to infinity of root x over x, you get 0. And so that is a little bit more precisely what he means by the answer is 0% of all natural numbers are perfect squares. In a very similar way, I could change that, or we could change that condition of natural numbers to about prime numbers. And so very similarly, 0% of all natural numbers are prime as well. Now in the bottom, what are we going to ask about? I'd like to know, well, how many natural numbers less than or equal to x are actually prime? Can I count them? And what we'll do is we'll define this function. This function's name is pi of x. And what pi of x does is it computes the cardinality of the set of all natural numbers such that you're a natural number less than or equal to the input x that's prime. And so to give you an example of how this function works, pi of 6 it should count the number of primes that are less than or equal to 6. And that's what this says. Count how many there are. And so I see that there's 1, 2, 3 of them in that case. And similarly, something like pi of 9 would tell me to count the number of primes less than or equal to 9. And so I'm thinking 2, 3, 5, and 7. So pi of 9 equals 4 because there's 4 things in that set. So pi is this function again that counts how many primes are less than the input of the function. You might have seen something similar to this if you've seen some modern algebra with Euler's phi function, which counted the number of integers that are relatively prime to a given integer and less than that. So maybe you've seen like phi of n, and to give you an example there, something like, let's see, phi of 6. The numbers that are relatively prime to 6 would just be what? Really just 1 and 5, right? So phi of 6 should be 2, right? And so anyway, this pi kind of works the same way as that phi does. If you've never seen that phi before, what the hell are you talking about? It's okay, we'll look at it later. So for pi right now, we're going to look at this pi function a little bit closely here. Sage actually has it built in. So prime pi is how you call the pi function. And so you see prime of 6 spits out 3. And similarly, it can compute some bigger numbers too. Prime pi of 100 is 25, and prime pi of, 3 million is 216,816. So how should you read maybe that last output again? I'm saying that there are 216,816 prime numbers less than or equal to 3 million. And what else can we do? We can plot what does pi of x kind of look like. And so I think I've got CoCalc up here, and so this is also a good instance to demonstrate. Sage has some cool plotting abilities as well. So, and it's just a command like plot, and you tell it what's your function. So the function's built-in name is prime pi, and we're going to tell it kind of the range that we're looking for, range of x values, I should say. So maybe a better word for that is what's the domain. So we're going to go maybe from 1 to 1,000, say, and that's enough for now. And so I'll have it run it. We'll let it think for a minute, and so that's what this pi function looks like. And as you see, how you should read this graph is there are a little bit over 160 primes that are less than or equal to 1,000. And maybe if I did, I guess it did prime pi. No, we didn't do that. So prime pi, goodness, prime pi 1,000. What's it say it actually is? Oops, it didn't like that, did it? Oh, I put some kind of a weird symbol in front of it, I think, like a goofball. Let's try again. Prime pi. I guess let me get rid of that nonsense. Cool. Yeah, I don't know what that vertical line is in front. Let's try again. Prime pi 1,000. Cool. And there's 168, which it looks like it fits with my graph. Yeah, a little bit over 160. Pretty cool. So let's go back to the notes in here. What we're going to do is, well, first here's this incredible fact. Gauss, he was alive in the 1700s. He himself was like a computer, and he wrote in 1800s as well. And he wrote in this 1849 letter that he thought that there were 216,745 primes less than 3 million, which is incredible because we know the exact number is 216,816,000. And so what I'm asking you to do is, this is what Gauss computed by hand in 1849. Look at how damn close he was. That is just incredible. So moving along, here's another graph of like we looked at earlier too. What's the point of this? Here's this thing that's called the prime number theorem. And what the prime number theorem says, it must be important. I mean, a lot of number theory is about study of the primes. Here we go. The function pi, which counts the number of primes less than or equal to x, is what's called asymptotic to the function x over log of x. And what does this asymptotic mean? What's it mean to say these two functions are asymptotic to each other? It means that if I took the limit of their quotient, that it goes to 1. And how you should think about that is, eventually, these two functions look the same, is how you should think about that. And that's what it means to be asymptotic. And so another way to interpret that then is that for large enough values for x, if you wanted to know the number of primes less than or equal to x, you could just figure out what is x divided by log of x, and that would give you a really good estimate of how many primes are less than x. So in particular, if you wanted to know, say, how many primes are less than 1,000,000, a really good estimate to the number of primes less than 1,000,000 would be 1,000,000 divided by log of 1 million. And when I write log, I mean base 10 here. So I need another 0 somewhere, don't I? Gosh, writing million's hard. Did I get it right up there? I did. So that would be a pretty good estimate to how many primes are less than 1 million. So again, the number of primes is pretty close to this function x over log of x. So that gives us a way to try to give a good estimate again about how many primes are less than a given x. And I'll scroll down a little bit. So a lot of these are details that maybe we won't ask any like homework questions over, but this is just kind of fun and some really big results in number theory. But as far as like record counting, the record for counting primes that a computer could do, like with pi, you could do 10 to the 23rd. I have no idea what that number is. It's too big. But that's a lot of primes, less than this number, 10 to the 23rd. And then now we get down to some good stuff about this really famous function called the Riemann Zeta function. The rest of this stuff has to do with a little bit of complex analysis. I'm not going to get very far into it. If you've taken a complex analysis course, you might be able to follow along to at least understand a little bit of what the zeta function is or what the theorem's talking about. It itself, though, uses some stuff that's in maybe a more advanced complex analysis class instead of just coming out of one where you kind of got used to derivatives and whatnot and with complex variables. But there is an excellent link to a video in the description that has really cool pictures and does a really cool explanation of what's going on with the zeta function. But so the zeta function is denoted by zeta of s. S is a complex number like a plus bi. And what is it? Is a complex analytic function, which in some sense means you can take its derivatives, but it's a little bit more than that. Analytic's a very strong word if you take a complex analysis class. Its domain is all the complex numbers except for one. And what this function does, what the zeta function does, is it extends, I'll scroll past this stuff, it extends this infinite sum here, n to the minus s. And this is a little bit goofy because s is a complex number. So if you've taken complex analysis, you're okay with, or you might remember, what's it mean if this is a complex exponent? Like what is something like 1 to the 1 plus I power? You might remember how to get into that. And then also too, like, if s is a number that's say like bigger than 1, this is just kind of a series from Calc 2, say, if you like. And so the Riemann hypothesis is that the continuation of this function has all of its zeros, its intercepts, if you will, in the complex plane, that they all lie on this vertical line whose real part is a half. And if you can prove that, you get $1 million. And maybe that should be your final exam question. You prove it. Since I suggested it to you, naturally you'd split the money with me. So what do mathematicians want to do? Like, we have not proved that at all. That's why it's an open problem. That's why somebody would get $1 million if they solved it. So what mathematicians typically try to do is to, formulate the problem in a different way. Find some characterizations of the problem at hand. And so one characterization of the Riemann hypothesis is it'd be equivalent to show that, that this integral here is another good approximation of pi of x. And what do we mean by good approximation here? Good approximation meaning that the difference between pi of x and this integral is less than or equal to root x times log of x. So if that was able to be proved for all x greater than 2.01, then what we're saying is you have proved the Riemann hypothesis as well. And so that's the connection between the Riemann hypothesis and the prime numbers. It's not so much a direct connection between this formula that shows up in the Riemann hypothesis with the zeta function. It's more, again, kind of a roundabout characterization that links the two concepts together. And then really the rest of the section is to just show some of the graphs. So P is the plot of this integral function above here. So again, this is a function where the input is the top limit of integration here, and just spitting out what that integral is. And we're just comparing it to the plot of our pi function, and then also comparing it to the plot of the square root of x times log of x. And let's see, that is the thing that's red. And what we're trying to show is that these two here, which is this much right there, they're all very, very close to each other, right? And the difference between those two functions is certainly less than the height of this red function. And again, so it looks like in a picture that this equality, or this inequality rather, it looks like it's pretty true. It looks like it's very, very, very true. That is the end of this section.